You're looking at an electromechanical crossbar switch running through a scanning cycle. Electromechanical crossbar switches offer the following admirable features: fast operation, a high degree of mechanical reliability, minimal mechanical motion, high quality electrical contact conductance, a very long lifespan in terms of its number of operations capability, and minimal maintenance. That's why they were used in large numbers of telephone systems all around the world. The first patent that I know of for an electromechanical crossbar switch was issued to a Bell System engineer named John Reynolds in 1915. However, the credit for building the first crossbar switch and then actually using it in a telephone switching system goes to Swedish telephone engineer Gotthilf Bettulander, who successfully achieved this in 1919. Despite Reynolds' patent, the Bell system didn't begin sustained development work on crossbar systems until 1930, when they finally became aware of Bettulander's switch. The first Bell system crossbar switching system went into service in 1938, designated appropriately as the number 1 crossbar system. My demonstration crossbar switch, shown here, is one of the Bell System designed switches. The Bell System code identifier for this switch is type 324P, which is just one of nearly 200 crossbar switch variants listed in the Bell System practices for the 300 series of crossbar switches. Both Western Electric and later Northern Electric manufactured these crossbar switches. This particular one was manufactured by Northern Electric in the second quarter of 1975. The construction of this switch is really heavy duty. The framework and vertical supports are 11 gauge steel, which is 1/8 of an inch thick, and so the switch is quite heavy, weighing in at 30 pounds. It's 20.5 inches long, 9.25 inches high, and 5 inches deep. There are 2 basic sizes of the 300 series of crossbar switches. My demonstration switch is the 10 vertical version, and this picture depicts the much more commonly used 20 vertical version. The 20 vertical version weighs 55 pounds. The switch has changed very little since the early 1938 version, shown here. In technical terms, a crossbar switch can be defined as a rectangular coordinate grid. Here is what a 10 by 10 rectangular grid looks like diagrammatically. Simply put, the crossbar switch is a coordinate gridwork of electrical circuit pathways. It has 10 horizontal rows on the grid, which are numbered from the bottom up, 0 through 9. It has 10 vertical columns on the grid, which are numbered left to right, 0 through 9. A coordinate point is where a horizontal row and a vertical column intersect. In crossbar switching systems, the word cross point is used instead of coordinate point. Any particular cross point is defined by its horizontal row number, followed by its vertical column number. This crossbar switch has 100 cross points, numbered 00 to 99. At each cross point, a vertical electrical circuit pathway intersects with a horizontal electrical circuit pathway, but in their normal or idle state, they remain electrically isolated from each other. Here is a close-up look at just one of the cross points on this switch. The circuits on a crossbar switch can consist of anywhere from 3 wires to 6 wires. On this switch, the circuits are 6 wires. In addition to its code type, a switch is designated by its number of cross points and the number of pairs of wires connected at each cross point. So this switch is called a 100-point 6-wire switch. At the cross points, the 6 wires of each horizontal circuit terminate on these 6 thin, flexible contact assemblies. From now on, we'll refer to these as the movable contacts. The 6 wires of each vertical circuit terminate on these 6 thick, rigid contact assemblies. From now on, we'll refer to these as the stationary contacts. A crosspoint has two electrical status conditions, open and closed. When a crosspoint is open, there is no electrical connectivity between its horizontal and vertical circuits. When a crosspoint is closed, it does have electrical connectivity between its horizontal and vertical circuits. When a crosspoint is in its idle position, it is open, which is what you're looking at here. The term non-operated is generally used to refer to an open crosspoint. When a crosspoint is in its in-use position, it is closed, which is what you're looking at here. The term operated is generally used to refer to a closed crosspoint. Crosspoint operation is performed by electromechanical activity, which is controlled by external common control circuits. The crossbar switch itself is just a dumb switch and has no control circuitry built into it. It just does what it's told to do. When a crosspoint is to be operated, electromechanical activity causes the movable contacts to be forced to shift to the left, such that they make firm contact with their mate stationary contacts. This completes an electrically conductive path between the horizontal and vertical circuits at this crosspoint. Here you're watching a crosspoint being operated and released several times. When we talk about circuits, we are referring to any type of electrical circuit that is external to the crossbar switch, but which has wires extending to and terminating on the crossbar switch. This would include such items as lines, trunks, and common control circuits. On this particular demonstration switch, each external circuit has 6 wires terminating either onto the stationary contacts of a crosspoint or onto the movable contacts of a crosspoint. For example, here we see 2 external circuits called Circuit A and Circuit B. Circuit A has a 6-wire connection terminating on the movable contacts of a crosspoint. Circuit B has a 6-wire connection terminating on the stationary contacts of that same crosspoint. If I want to connect Circuit A to Circuit B, I can do so by simply operating that crosspoint. You'll notice that for each pair of contacts, there are actually 2 points at which contact is made, once near the top and once near the bottom. This is called contact twinning, so at any given crosspoint, there will be 2 contact points on each of the 6 stationary contacts and 2 contact points on each of the 6 movable contacts. This does not mean that the movable contacts are connecting 2 different circuits to the vertical contacts. It's just that the last inch of the movable contact springs that lead up to the contact points is bifurcated. That is, it's divided into 2 tines, as can be seen here from this side view of a vertical unit. With this arrangement, a speck of dirt on one contact point won't hinder the other contact point from closing. With twin contact points, the probability of a failure to achieve a successful operation is 1/50th the failure rate of a single contact point. The contact points on all crossbar switch contact springs are tiny rectangular shaped precious metal bars welded onto the stationary and movable contacts, as can be seen here. They are made of nickel topped with a layer of palladium, which is a member of the platinum family of metals. On cross points, the contact point bars on the stationary contacts are positioned vertically, while the ones on the movable contacts are mounted horizontally. When 2 contact points close, they form the shape of a cross, as can be seen here. This allows for considerable misalignment tolerance, as shown in this diagram. It would be possible to construct a crossbar switch that would have 100 vertical circuits and 100 horizontal circuits, with each circuit appearing at only 1 cross point on the switch, as can be seen in our original grid diagram. With such an arrangement, however, each circuit would be limited to connection to only one other circuit. It is usually desirable to increase access flexibility at the expense of reducing the total number of circuits on the switch. In the Bell system, the 300 series of crossbar switches are all designed so that on each vertical column, the stationary contact assemblies are multipled from the bottom of the switch vertically upwards through all 10 horizontal rows. The grid diagram for that configuration looks like this. The solid vertical lines indicate that there is only one circuit per vertical column. So on our demonstration crossbar switch, there are actually only 10 vertical circuits. This vertical multipling is built into the switch design and is not alterable. Here's a vertical unit that has been removed from the switch. So far, we had only looked at the stationary contacts in isolation on one crosspoint. Now we can see that they are in fact solid brass bars that extend vertically upwards through the full height of the switch vertical unit. Here's a view of the left side of a vertical unit. On the far right, you can see the leftmost of the 6 vertical brass bars that extend the entire height of the vertical unit. Notice that the brass bar extends below horizontal 0. This provides a location for test access to the vertical unit. Just to the left of the stationary vertical brass bar, you can see the leftmost of each of the 10 horizontal movable contact assemblies, numbered 0 to 9 from the bottom up. Here's a view of the rear of a vertical unit. You can see all the individual vertical and horizontal wire wrap type terminals, starting at the bottom are the holding off normal contacts, the 6 stationary vertical contacts, the 6 horizontal movable contacts for horizontal 0, horizontal 1, and continuing upwards through horizontals 2 to 8 and finally horizontal 9. These fork-tipped projections on each horizontal movable contact spring are for insetting and soldering horizontal multiple bare strap wires that we'll be looking at shortly. Here's a view of the right side of a vertical unit. It's dominated by the heavy-duty vertical unit support frame. On the far right are all the external circuit wire termination points that we just looked at on the rear vertical view. All the wires for the vertical and horizontal circuits would be attached to these terminals by using a special wire wrapping tool that wraps the wires in tight coils around the terminals, as can be seen here. All crossbar switch connections are wire wrapped, except for these horizontal bare strap wires, which are soldered connections. Okay, we finished discussing the vertical circuit wiring. Let's turn our attention now to the horizontal circuit wiring. Here's a rear view of the demonstration crossbar switch. You can see the 10 vertical units. They're numbered 0 to 9 from right to left. I'm going to do a close-up scan of the rear view of the switch, starting at the right end. First, let's look at these last 2 verticals, which are verticals 8 and 9. None of the movable horizontal contacts has any factory-provided multiple wiring on any row. So the 10 sets of horizontal movable contacts on vertical 8 can be wired to 10 different external circuits. If I also wired a vertical circuit to the stationary contact multiple of vertical 8, it will have access to 10 different horizontal circuits that it does not have to share with any other vertical circuit. This exact same arrangement will also apply to vertical 9. Now let's look at verticals 6 and 7. On every horizontal row, the movable contacts on vertical 6 have been strapped to vertical 7. You can see 6 bare straps soldered to the rear terminals of the movable contacts on vertical 6, strapped over and soldered to the light-numbered movable contacts on vertical 7. This is called horizontal multipling. Now, if I actually wired 10 external horizontal circuits to the movable contacts on vertical 6, the same 10 horizontal circuits would also be connected by these straps to the movable contacts on vertical 7. If I also wired an external circuit to the stationary contact multiple on vertical 6 and a different external circuit to the stationary contact multiple on vertical 7, these 2 external vertical circuits would have to share their access to the same 10 horizontal circuits. This same sharing arrangement is repeated for verticals 4 and 5, 2 and 3, and 0 and 1. In this picture, the 10 horizontal red lines each represent a 6-wire bear strap multiple. This multiple extends across all 10 verticals. With this arrangement, the switch could only have 10 horizontal circuits in total. Each vertical circuit would have access to all 10 horizontal circuits, but would be sharing that access with the other 9 vertical circuits. The horizontal multipling arrangement shown here is the most common one used in crossbar switching systems. Horizontal multipling is fully flexible because the soldered bear strap multiple wiring can be added, deleted, or extended to suit any application. It can also be field modified even after the switch has been installed in a central office. So we finished examining the structure of the vertical units, the arrangement of the horizontal and vertical multipling, and the details of the cross-point contact assemblies. The next question that needs answering is, how do we operate this cross-point electromechanically? Well, let's begin by comparing the motion of a cross-point to the motion of the contact springs of a relay. First, we'll look at the operation and release motions of a cross-point. Now we'll look at the motions of the contact springs of a relay in a step-by-step switch. The motions of the cross-point contact springs and the relay contact springs are quite similar. In the relay, however, this motion is caused by the energizing of this electromagnet, which attracts this armature, which in turn moves the contact spring set. But when we look at the cross points on a crossbar switch vertical unit, we see that they don't have their own electromagnets or armatures. Instead, a 100 cross-point crossbar switch has only 20 electromagnets. These are detached from proximity to the cross points and are located in the positions enclosed by the red and green rectangles in this view. These 20 electromagnets activate small motions on mechanical linkages to operate crosspoints. It is this arrangement that gives the crossbar switch a decided advantage over an all-relay system. The crossbar switch has two functional types of electromagnets, the selecting magnets and the holding magnets. The selecting magnets are enclosed in the red rectangles, with their armatures positioned directly in front of them. The holding magnets are enclosed inside the green rectangle, also with their armatures positioned directly in front of them. The selecting magnets are located at each end of the switch, with 6 at the left end and 4 at the right end. Here's a close-up view of the 6 selecting magnets at the left end of the switch. Each selecting magnet is assigned to function with a particular horizontal row on the switch. As such, each magnet is identified by the horizontal row number to which it is assigned. The 6 selecting magnets shown here are arranged in 3 pairs. The first pair contains selecting magnets 0 and 1. The second pair contains selecting magnets 4 and 5. And the third pair contains selecting magnets 8 and 9. In the picture, it may seem that the horizontal assignments of the selecting magnets are out of sequence, but this is due to the toggling arrangement of the armatures, which we'll be looking at shortly. The 4 selecting magnets at the right end of the switch are arranged in 2 pairs. The first pair contains selecting magnets for horizontals 2 and 3, and the second pair contains selecting magnets for horizontals 6 and 7. The selecting magnets on this switch each have a resistance of 600 ohms. They are energized by applying 48 volts DC across the windings. Operating time of the armatures is about 25 milliseconds. There are 5 long horizontally mounted bars that traverse the full width of the switch. These are called selecting bars. They are made of heavy gauge steel. Here's a close-up view of a selecting bar that has been removed from the switch. Attached at one end of each selecting bar is a double-headed or butterfly armature. A close-up of this armature is shown here. Each of these selecting bars is associated with a particular pair of selecting magnets, and in turn, the two horizontal rows that those selecting magnets control. Each selecting bar is positioned to lie just between its two selecting magnets. The lowest selecting bar has its armature at the left end and is associated with horizontals 0 and 1. The second selecting bar has its armature on the right end and is associated with horizontals 2 and 3. The third selecting bar has its armature on the left end and is associated with horizontals 4 and 5. The fourth selecting bar has its armature on the right end and is associated with horizontals 6 and 7. And finally, the fifth selecting bar has its armature on the left end and is associated with horizontals 8 and 9. A selecting bar is held in position by two of these pivot screws, one at each end of the bar. Here you can see 5 of the pivot screws mounted at the left end of the switch. The smooth cylindrical shaped ends of the pivot screws extend into holes in these black colored bearings attached to both ends of each selecting bar. The selecting bars are mounted with a small amount of lateral play so that they are free to pivot from their rest position in a 10-degree upward or downward arc. This would occur if either of a selecting bar's two selecting magnets were energized. An energized selecting magnet attracts the armature that is positioned in front of it. If the lower selecting magnet of any pair is energized, it attracts the lower armature on the selecting bar, which causes the selecting bar to tilt upwards. If the upper selecting magnet of any pair is energized, it attracts the upper armature on the selecting bar, which causes the selecting bar to tilt downwards. On each of the side faces of the crossbar switch, there are sets of contact spring assemblies. There is one spring assembly for each pair of selecting magnets. So there are 3 spring assemblies on the left side of the switch that you can see here, and 2 on the right side. Let's take a close-up look at one of these spring assemblies. When not operated, a selecting bar is kept centered in its normal rest position by these 2 tensioned centering springs. Each selecting bar's double armature is equipped with a stud mounted on a lever. That stud fits in between the 2 centering springs, and the tension of the springs retains the stud and its associated lever, double armature, and selecting bar in their normal centered idle position. When an upper selecting magnet of a pair is energized, its armature operates. The tension of the centering springs is overcome, and the stud arcs downwards in concert with its armature. This motion causes a set of selecting off normal springs to operate. When a lower selecting magnet of a pair is energized, its armature operates, and its stud arcs upwards. Again, this motion causes a set of selecting off normal springs to operate. The operation of selecting off normal springs closes an electrical path to an external circuit. The function this provides is application specific. Along the length of each selecting bar are these 10 evenly spaced wire protrusions. These are spring-tensioned steel wires called selecting fingers. They are 2 inches long and are mounted at right angles to the length of their selecting bar and horizontally in line with the top and bottom faces of their selecting bar. One end of each selecting finger has a coil that screws onto a mounting stud on the inside face of its selecting bar. The horizontal position of the 10 selecting fingers on a selecting bar is midway between the 2 horizontal rows of cross points associated with that selecting bar. Their vertical position is just to the right of each of the 10 vertical units. Notice that when the lower armature on a selecting bar operates, that bar's 10 selecting fingers all tilt upwards along with the bar. Similarly, when the upper armature on a selecting bar operates, that bar's 10 selecting fingers all tilt downwards along with the bar. Before we describe the actual purpose of these selecting fingers, we need to learn all about the holding magnets and their armatures. Associated with each vertical unit is an electromagnet called the holding magnet. The holding magnets are located at the bottom and to the right of each vertical unit. So this switch has 10 holding magnets that can be seen here behind their armatures. They are numbered 0 to 9 from left to right. From the rear view of the switch, you can see that the holding magnets are held in position by one screw that firmly attaches them to a half cylindrical shaped bracket on the support frames of the vertical units. Here's a holding magnet that's been removed from the switch. Its resistance is 1250 ohms and it's normally operated by applying 48 volts DC across its winding. With this voltage applied, the operating time of its armature is 55 milliseconds. In some applications, 178 volts DC is applied across its winding, which speeds up its armature's operation to 18 milliseconds, which is about 3 times as fast. The expensive common control equipment that oversees the operation of a holding magnet has to wait to confirm its successful operation. The shorter the operating time, the shorter will be the overall holding time of the common control equipment, and the quicker it will become available to serve other calls. Associated with each vertical unit is a holding armature that is positioned directly in front of its vertical unit's holding magnet. Here's a holding armature that has been removed from the switch. Holding armatures have long arms that extend vertically upwards, passing by all 10 horizontal rows of crosspoints. The mounting arrangement of a holding armature to a vertical unit is a very clever design in that it's simple, inexpensive, requires no precision, and works extremely well. Near the bottom of the armature is this small aperture. Near the bottom of the vertical support frame, there is this bearing support lug. This lug supports the weight of the armature and provides narrow limits for the armature's sideways or backwards motion. The aperture on the armature simply fits over this bearing support lug. The top end of the armature has an open-ended notch or slot. Near the top of the vertical support frame is this letter C shaped armature bearing lug. This lug provides narrow limits for the armature's sideways or backwards motion and stops it from falling forwards. The notch in the armature simply slides into the opening in the bearing support lug. The loose fitting arrangement between the armature and the bearing lugs allows the armature to easily pivot about its axis. This is an aluminum armature retaining lug and backstop that has been removed from the switch. There is one of these per vertical unit, so 10 in all for this switch. It mounts to the vertical support frame and can be adjusted forwards and backwards by this slotted mounting fork. Here is how it appears in its mounted position. This part is the armature retaining lug that stops the bottom of the armature from falling forwards off its bearing support lug. This part is the armature backstop, which provides the rest position for the armature in its non-operated state. Each holding armature is equipped with this lever and stud, and each vertical unit is equipped with this balancing spring. When an operated holding magnet is de-energized, its armature is returned to its rest position against the backstop by the tension of this balancing spring pressing on the armature's stud. When a holding armature operates, its lever and stud operate a set of holding off normal contact springs. This opens or closes electrical paths to external circuits, and the functions that this provides is application specific. The arrangement and number of these contact springs varies with the type of crossbar switch. For each vertical unit, there are 5 selecting fingers, one on each selecting bar, which in their idle state will be projecting into gaps at the right side of the vertical unit. When a holding armature operates, its long extension arm swivels and pushes against these 5 selecting fingers, deflecting them to the left. Here's a close-up of just one selecting finger's motion when a holding armature operates. Notice that on a vertical unit, every cross point has one of these black inserts that spans across the full width of the vertical unit. These inserts are made of an electrically insulating material, probably plastic or nylon, and are called operating cards. Here's an operating card that has been removed from its vertical unit. It has 6 upper and lower pairs of notches. At a cross point, the 6 movable contact springs reside in the notch spaces, with their top tines in the upper notch spaces and their bottom tines in the lower notch spaces. The movable contact springs are pre-tensioned to rest as far to the right as possible, so that they butt up against the left edge of each notch projection. The rightward motion of the operating card is limited by its leftmost notch projection, which butts up against the leftmost stationary contact vertical bar. I can manually move an operating card to the left. When I do so, the 6 movable contact springs entrapped in its notches are also forced to move to the left, along with the operating card. This causes the movable contact points to close against the stationary contact points at this cross point. The right end of each operating card has 3 distinct edge surfaces. It has a horizontally aligned stop edge, a vertically aligned operating edge, and a diagonal non-operating edge. A selecting finger in its normal rest position resides here, aligned with the diagonal non-operating zone of its 2 operating cards. If its holding armature operates, it just moves leftwards into the non-operating zone. If the lower selecting armature associated with a selecting finger's selecting bar is operated, the selecting finger will tilt upwards and come to rest on the stop edge of its upper operating card. If the upper selecting armature associated with a selecting finger's selecting bar is operated, the selecting finger will tilt downwards and come to rest on the stop edge of its lower operating card. If a selecting magnet is energized, its selecting armature will operate, and the 10 selecting fingers on the selecting bar will tilt and come to rest on the stop edges of their operating cards. If, during the time interval that the selecting magnet remains energized, any holding magnet becomes energized, its holding armature will operate and move its 5 selecting fingers to the left. 4 of these selecting fingers will enter the non-operating zone of their operating cards. However, the 5th selecting finger is resting on the stop edge of its operating card. So at this cross point, the operation of the holding armature will force the selecting finger to push on the operating edge of its operating card. This will force the operating card to move to the left, pushing its 6 movable contacts with it. This will cause the movable contacts to mate with their stationary contacts. Finally, we have electromechanically operated a cross point. So here's a typical sequence of events for the operation of a cross point. A common control circuit has chosen a cross point that it wants to operate. Let's say it's cross point 0, 0. The common control circuit energizes the select magnet for horizontal 0. The selecting armature operates, and all 10 selecting fingers tilt downward and rest on the stop edge of the horizontal 0 operating cards. The common control circuit energizes the holding magnet on vertical 0. When the holding armature operates, it causes the cross point on horizontal 0 to operate, because the selecting finger is resting on the stop edge of its operating card. The remaining 4 selecting fingers move to their left into their non-operating zones. The common control circuit de-energizes the selecting magnet, its associated selecting armature, selecting bar, and 9 of the 10 selecting fingers return to their normal position. The selecting magnet is de-energized very quickly because 1, it's no longer needed, 2, it makes the 9 remaining selecting fingers on the selecting bar available for subsequent requests for service, and 3, it prevents double connections. The 10th selecting finger is the one being used at the operated cross point. The operated holding armature keeps it held pinned against the operating edge of its operating card. Let's take a close-up look at that sequence of events. So here we're looking at an operated crosspoint with the selecting finger clamped in position between the operating edge of the operating card and the holding armature. The selecting magnet is still energized, and so the selecting armature is operated and the selecting bar is tilted downwards. Now watch what happens when I de-energize the selecting magnet. The selecting armature will release and the selecting bar will tilt back to its rest position. But notice that the selecting finger is still firmly clamped, holding the crosspoint operated. One operated crosspoint on a crossbar switch doesn't make that switch unavailable to serve other calls. Let's look at an example of a 100-point crossbar switch that has 10 vertical circuits and 10 horizontal circuits. If all 10 vertical circuits were in use, then all 10 holding armatures would be operated, as can be seen here. In addition, there would be 10 crosspoints operated, one on each horizontal row, as can be seen here. Crosspoint 00, crosspoint 11, crosspoint 22, crosspoint 33, crosspoint 44, crosspoint 55, crosspoint 66, crosspoint 77, crosspoint 88, and crosspoint 99. The particular 10 crosspoints operated would not necessarily be in the sequence that was shown here. Okay, now let's see how an operated crosspoint is returned to its non-operated position. When the operated crosspoint is no longer required, the holding magnet is de-energized. The tension of the balancing spring returns the holding armature to its normal rest position against its backstop. This allows the tension of the movable contact springs to shift themselves and the operating card back to the right, opening the crosspoint. Notice that the freed up selecting finger has also returned to its normal position, aligned with the non-operating zone of its two operating cards. You may have noticed that each selecting finger has attached near its base one of these little spring assemblies. These are called damping springs. When a selecting finger at an operated crosspoint is released, it tends to oscillate. If its holding magnet is re-energized very quickly, it is possible for an oscillating select finger to be caught inside the operating zone of its operating card and unintentionally reclose the contacts at its horizontal. This would result in two crosspoint closures, the intended crosspoint and the unintended crosspoint. This trouble condition is called a double connection. To prevent this from happening, a damping spring is utilized, which reduces the oscillations of its selecting finger and brings it quickly to rest. We're going to take a brief look at the applications of the crossbar switch in the number 5 crossbar switching system. This is an analog relay-based common control switching system. The number 5 crossbar system was first put into service in 1948. By 1978, it was serving more subscribers in the Bell system than step-by-step equipment. By the end of the 1990s, it had been phased out in favor of digital switching systems. It has two main common control call setup devices, the dial tone marker and the completing marker. In addition, there are several types of common control ancillary devices, such as originating registers, incoming registers, and outgoing senders. I'm just going to provide an overview of the relationship between the common control devices and the crossbar switches in the number 5 crossbar system. And by the way, a typical 10,000 line number 5 crossbar system would have in the neighborhood of 1,000 crossbar switches. Just to give you a frame of reference, all the bays of number 5 crossbar equipment that you'll be looking at, including the ones you're looking at right now, are 11.5 feet high. Here's a photo of an early version of a dial tone marker. It has around 500 relays. When a subscriber wants to originate a call, a dial tone marker sets up a connection through the crossbar switching network from the subscriber's line to an originating register. An originating register sends dial tone to the subscriber and receives and stores the dialed digits. It takes a dial tone marker about a quarter of a second to set up a connection. A typical 10,000 line office would require 2 dial tone markers. The maximum is 6. Here's a photo of a completing marker, which has about 1,500 relays. It sets up all outgoing, incoming, intra-office, and tandem call connections through the Crossbar switching network. The completing marker takes about a third to half a second to set up a call. A typical 10,000 line office would require 4 completing markers. The maximum is 12. In the number 5 crossbar switching system, the voice transmission path switching network is a gridwork of crossbar switches. It contains 2 major frame types: line link frames that you're looking at now, and trunk link frames. Every switching network connection is between a line link frame and a trunk link frame. Line link frames contain 2 types of switches: line switches and junctor switches. Every subscriber line is terminated on a vertical on a line switch. Junctors are 3-wire transmission paths that interconnect line link frames and trunk link frames. Each junctor terminates on a vertical on a line link frame junctor switch. Lines are connected to junctors by means of line links, which are transmission paths that terminate on the horizontals of both the line switches and the junctor switches. A line link frame may contain more than the 2 bays shown here. The line capacity of a line link frame ranges from 190 lines up to 590 lines. A typical 10,000 line office would have 21 line link frames of the 490 line capacity size. The maximum is 60 line link frames. Trunk link frames contain 2 types of switches: junctor switches and trunk switches. Junctors coming from the line link frames terminate on the horizontals of the junctor switches. All the various types of trunk circuits terminate on the horizontals of the trunk switches, along with the common control originating registers. Trunks are connected to junctors by means of trunk links, which are transmission paths that terminate on the verticals of both the junctor switches and the trunk switches. A trunk link frame has the capacity to terminate a maximum of 160 trunks and originating registers. A typical 10,000 line office would have 10 trunk link frames. The maximum is 30 trunk link frames. Here's a diagram depicting the connection between a subscriber line and a trunk circuit through the crossbar switching network of a number 5 crossbar switching system. A subscriber line terminates on a vertical on a line switch. An operated crosspoint connects it to a line link on the horizontal of that line switch. The far end of the line link terminates on a horizontal on a junctor switch. An operated crosspoint connects the line link to a junctor terminating on a vertical of that junctor switch. The far end of the junctor terminates on a horizontal on a trunk link frame junctor switch. An operated crosspoint connects the junctor to a trunk link terminating on a vertical of that junctor switch. The far end of the trunk link terminates on a vertical of a trunk switch. An operated crosspoint connects the trunk link to a trunk terminating on a horizontal of that trunk switch. The 4 crossbar switch holding magnets involved in this connection would remain operated, thus keeping the crosspoints closed, for the duration of the telephone call. This is an outgoing sender link frame which has the capacity to mount up to 10 crossbar switches. Outgoing trunks are terminated on the verticals of these switches, and outgoing senders are terminated on the horizontals. Each crossbar switch terminates 20 trunks on the verticals and 10 outgoing senders on the horizontals. Outgoing senders are relay-based common control devices that are utilized to outpulse the called telephone number digits to a distant office. On an outgoing call, a completing marker sets up a connection between an outgoing sender and an outgoing trunk by closing the appropriate crosspoint on an outgoing sender link switch. The outgoing sender outpulses the required digits through this outgoing sender link switch path through the outgoing trunk and towards the distant office. When the sender has finished outpulsing, it drops out of the connection, and the path through the outgoing sender link switch is released. So for this application, the crossbar switch connection is only maintained for a few seconds. This is an incoming register link frame, which has the capacity to mount up to 8 crossbar switches. Incoming trunks are terminated on the verticals of these switches, and incoming registers are terminated on the horizontals. Each crossbar switch terminates 20 trunks on the verticals and 10 incoming registers on the horizontals. Incoming registers are relay-based common control devices that receive and store in memory the called telephone number digits that are outpulsed from a distant office. On an incoming call, incoming register link control circuitry sets up a connection between an incoming trunk and an incoming register by closing the appropriate crosspoint on an incoming register link crossbar switch. The incoming register receives and stores the digits outpulsed from a distant office through the incoming trunk and through the incoming register link crossbar switch path. When all the digits have been received, the incoming register requests a connection to a completing marker and passes the received digits to it. The completing marker completes the connection to the called line, the incoming register returns to its idle state, and the connection through the incoming register link crossbar switch is released. So for this application, the crossbar switch connection is only maintained for a few seconds. This is an incoming trunk double bay relay rack frame, which has the capacity to mount up to 80 incoming trunks and 8 crossbar switches. On this frame, the crossbar switches function as ringing selection switches. A variety of coded ringing generators are terminated on the horizontals of the crossbar switches, and the incoming trunks are terminated on the verticals. When processing an incoming call, a completing marker sets up a connection between an incoming trunk and a particular code of ringing generator by closing the appropriate crosspoint on a ringing selection switch. The ringing generator current is passed through the ringing selection switch connection, through the incoming trunk, through the trunk link frame line link frame switching network path, and out to the called telephone. When the call is answered, the path through the ringing selection switch is released. This is a traffic usage recorder frame. This frame is not actually a part of the number 5 crossbar switching equipment, but would generally be found located inside the central office switch room. The purpose of the traffic usage recorder is to scan various components of switching equipment to see if they are busy or idle. The scanning looks like this. The TUR can scan 3,600 different circuits in 100 seconds. The results of the scans are utilized for traffic engineering of future switching equipment requirements and for office load balancing. This is the one application that I'm aware of in which the crossbar switch horizontals have no bear strap multipling at all. This brings an end to my video on the telephone system crossbar switch. The fact that you're still watching indicates you have a keen interest in the subject matter. I hope you found it informative and easy to understand. If you have any questions, please put them in the comments area of the video and I will attempt to answer them. Thanks for watching.